Last time we introduced the radiation integral. Last time we introduced the radiation integral, where the magnetic vector potential at some observation point is equal to an integral over the extent of any sources of the electric current density, where the primed coordinates show you where the sources are, times a phase term, e to the minus jk times the distance between the observation point and the source point, divided by a spherical spreading out term, same distance, over volume times some constants at the front. Physically, this makes sense. We're essentially summing the contributions from each infinitesimally small element of this current distribution at the observation point and saying that the sum of all of those contributions turns out to be the total field, which is true anytime you're in a linear system that obeys superposition because it's linear. However, actually evaluating this integral, especially in a closed form by hand with pen and paper, is kind of a pain because this radiation integral has this term in it. And this term turns out to be the square root of a bunch of things that are squared, so it might look like this in Cartesian coordinates. Or in spherical coordinates, it would look like this. Where I am using r and r prime without the arrows on top to denote the magnitudes of those two vectors. And psi here is the angle between r and r prime, the observation point vector and the source point vector. So this is a pain to evaluate, but maybe it could be simpler. Usually in an antenna situation, the observation point is much farther away from the origin of your coordinate system than a point that's still physically on the antenna. So in that sense, r is much greater than r prime. That kind of makes sense. If the receiver was right next to the transmitter, you could just hand them your message or say it to them. You wouldn't actually need to use an antenna in the first place. Let's look at this with a diagram. Let's say we've got some sources over here. And let's say we have an observation point all the way over here. How can we simplify this situation? Well, let's look at a line from two different points on the source distribution. We can even make them maximally far apart to this observation point. I missed a little bit. We'll just make the observation point bigger. There we go. Now, if you look at it over here, these two lines, they're nearly parallel, right? which means they're almost the same length. For amplitudes, we can actually make the approximation that for any value of r prime that exists on the source, one over the magnitude of the distance between the source point and the observation point is approximately just equal to 1 over r. The distance from the origin, let's say it's at the center of our antenna, although we don't really care, to the observation point. This kind of makes sense. Your antenna's extent is probably a wavelength or a few wavelengths or even several wavelengths, but in general you are many, 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 many wavelengths away. And this depends monotonically on r. It doesn't have any oscillatory behavior, and as r gets bigger, small differences in the size of r don't affect it very much. But for the phase term, because remember we also have e to the minus j k magnitude r minus r prime in that radiation integral, for the phase term, we actually do care about small variations in that magnitude term, because this varies pretty quickly. And that variation doesn't get slower just because r is large. Or rather, it doesn't depend less on r prime just because r is large. That doesn't mean we're out of luck, though. This part here, where I say that those two lines are nearly parallel, that's going to be the key. Let's look at that situation again. Let's say we've got the origin here and another point on our source distribution over here. So like that's the origin, and let's say that this is r prime. And we'll draw two lines over to some observation point very far away, and that's r. So this vector from the origin to the observation point actually is r itself. This vector is r minus r prime. What we want to know is, what is the difference in length between these two vectors? We can do that with triangles. We'll drop a perpendicular line from the r prime point onto that r vector. We will notice that the corner of this triangle is psi, the angle between the two vectors r and r prime. And then we'll try and figure out what this tiny distance right there is. What is that distance? Because that is the difference in length between just r and r minus r prime. It turns out, if you take a look and you know your right triangles, that distance is r prime cosine psi. So, if r is very large, that means that these two vectors are almost parallel, and this magnitude term of r minus r prime is approximately equal to r minus r prime cosine psi, where again psi is the angle between r and r prime.